right? So this results actually talk to us the normalized impedance, normalized by characteristic impedance of air or water, whatever medium, Yang-Hann. Okay. What is your impedance of your head motion? The pressure is very small, but the angular velocity of his head motion has finite value, right? So increase your impedance, infinity, then no motion, right? So I ask Yang-Hann to increase your impedance as much as you can. Okay? That is function of KR. That means it depends on, firstly, how far is he from the origin compared with the wavelengths. Right? Wow, that is interesting. And I can see that this has a real part and imaginary part. So I multiply 1 plus JKR in both sides. That gives me 1 plus KR square. And I am applying 1 plus JKR to here. That gives me minus JKR plus KR square. So rearrange this, give me 1 plus KR square to the KR square minus JKR 1 plus KR square. Is it minus? Monitor? Okay, thank you. Wow, this is, to me, frankly speaking, first time to not to make any error in deriving those results in 10 years. So I am very happy. So this is the real part. Okay, if KR is very large, it physically means what? Wavelength is small compared with when KR is very large, it means physically means what? Wavelength is small compared with R, right? Or when KR is very large, means that I am observing the field away, very far away from the origin. In this case, this is this approach to when KR is very large, 1. That means impedance is the same as the characteristic impedance of medium. That means plane wave. So in a far field that we call far field, in a far field, the wave field behaves as if it is plane wave field. But this one, approach to, when KR is very, very large, this one approach to 0. If you cannot imagine, just to put KR is 100, then this is 10,001. And this is 100. 100 is nothing, right, compared with 10,001. So you have a 10,001 and somebody has 101, and you will regard him nothing, right? Because he's so trivial money. So in a far field, there is no near field effect, of course. That means there is no reactive term. In other words, in those fields, when I oscillate the fluid just propagate with no phase difference, as we see for the infinite string case. With infinite string, the point impedance was rho 0 C, no imaginary part. Okay. But in the near field, that means when Kr is much, much smaller than 1, this one is what is it? Are we in the near field or far field? Depending on frequency, right? This one has okay. When Kr is very small, like 0.001, then this is 0, and this is 0.2. Yeah. Yeah. But the rate of decaying is somewhat different. So if we express those real term and imaginary term graphically, in terms of Kr, the real part looks like this. Okay. The imaginary part and real part has the same value when Kr equal to 1. That is 1/2. And the imaginary part look like this. And also note that ZR when NA equal R, when A equal A, that is what? That is the sort of driving point impedance of breathing sphere, right? And R equal A. That also look like this. Okay, that means this one is Ka square 1 plus Ka square Ka over 1 plus Ka square. What does it physically mean that when Ka is very large? That means wavelength is small compared with the diameter of breathing sphere. In other words, radiator's diameter. That means I have a sphere and I am radiating sound with a very small wavelength, right? Or very small omega. That means subwoofer.